Okay, so we are going to continue a little bit chapter 14, the partial derivative. So last time, yesterday, we discussed on the directional derivative and how to maximize the directional derivative. And by the way, I have checked your meter, so you can check later. And I think I will give you opportunity to have a makeup meter. So next week I will be not here, but I will have my DA to set up the makeup meter. But I think I will just write some questions that maybe only 3 to 4 questions. So maybe it only need to have only need 1 hour. Okay, 1 hour. So 2 questions from chapter 10, 2 questions from chapter 11. Okay. By default, maybe Wednesday morning, maybe. Okay. I will have announcement later. So you will have a TA class on Monday, and maybe the TA class can give some advice for the makeup intern. Okay? And it will be not as difficult as the one that you have, but still, the final result will be combination from your first and the second one. So maybe 40% plus 60. This is the old result and this is the new one. Okay. This is optional, but if you want, you can take it. So you can consider, put your score if you want. Because some of you are, I think I can say for our standard is quite okay, quite good. The average is 51 or 52. Okay, so if you get 60 or 70 or even 80, that should be fine. But if you below 40 or below 50 or below 40 or between or maybe below, then I think you need to take it. Okay, now let me continue a little bit. Okay. I will give you the score maybe around 6. Okay, around 6. So now, if we look here, and let's say the same surface, the blue is the surface, and then as also we discussed before, we have the tangent plane. Okay, the tangent plane on this point P. We have the tangent plane, and now actually we can set our definition first that the gradient factor of f that we set up in the directional derivative is actually our normal factor. This is the normal factor. Normal means it is perpendicular or 90 degree on this one. Okay, it's 90 degree on the plane. Okay. And then maybe let me write some notes on the right side so that we can know what is happening. Okay. So this is a surface S. Okay. So this is surface with equation 3 variables equal constant like that. Okay. So it means that from these equations, this is a level surface equation or level surface of functions with 3 variables. Okay. Let me put down that first. So first, we could set up the point B in the picture at x0, y0, and z0. Okay. on the surface, on surface S. And then we set up C, that is actually the curve that goes along the surface, and then pass through the point P. So this is curve S, or curve on S, that pass P. Okay. And this curve for the C is defined by parametric equation in vector or vector function. And this point P that's set up in x0, y0, z0, this is correspond to the t0. Okay, this is not to t0, which means that we can set our initial point at the x0, y0, z0 using our parametric t0. Okay. Now we can set up our surface, which is the first one. And let me rewrite again here. So since this is our surface, then we can set up the x as a parametric t like that. Okay. Equal a constant. And then we can partially derive with respect to t. Okay. So then for each one of them, we are going to have chain rule for parametric only. So dou f dou x dx dt plus dou f dou y dy dt plus dou f dou z dz dt. It's perfectly similar to what we have in the chain rule. Okay, if you remember that we need to draw the tree. So we start from f, so it's branched into 3, x, y, z, and then each one is going to t. So each one is one branch, second branch, the third. Okay. And then this equal to 0. Okay. So this actually, dx dt, dy dt, dz dt, we can think this is the first derivative from each parametric, right? Each parametric axis. And this partial is actually our gradient vector. So we can set up this as a multiplication of dot product. Okay. So this is a vector, this is also a vector from this one, okay, vector, the curve. So we can write this as and then dot with this. Okay. And this equal to 0. This is the del of f. This one is the r prime t. Okay. So it is actually refers to what we have in the picture. The dot product, which they have the 90 degree, is going to be 0, right? Because of the vector property. Okay. Because of this. So the theta is the angle between vectors. since the angle between vectors is 90, it's 0, right? So this is also proving from our side here that this is actually proving that this is 0. So which means we can write that the del f at point B is perpendicular to tangent vector r prime t. Okay, now to connect this to our general expression for tangent plane, okay, so let me rewrite here. So tangent plane to level surface f xyz equal k at P, which is we define as this point x0, y0, z0, is given by this. This f with subscript x means the partial. Okay? So we partially derive with x. So fy, fz also partial derived with y and z. So how to use this? So basically, if we know the function, we can derive the function, and we know the point, which means the partial x, we partial derive with x, so we get the equation, right? And then we put the point x0, y0, z0, any number, right? Any number, we can put the point. And then multiply with x minus the x, the number, and the same with y and z. So you will get the tangent plane equation directly. So it is more direct approach. So if you remember from the previous sections, we also have the tangent plane. You can choose like which one you want to approach. But this one can be applied for every aspect. Okay? So it's more general. So you can use this to find the tangent plane equation. So this we can also write in another simple way with the del f at x0, y0 dot product with r minus r0. From this equation, we can also write our normal line by taking this into this. This is we call the, if you remember, this is the symmetric equation. Okay, now just to make sure that we can apply this easily, so let me just get you to some example. So let's say we have x squared, so it's so we have a quadratic surface. Do you remember what's the name? Do you remember the name? It's all plus and then half squared. What it is? Yeah, ellipsoid. Okay, so let's say we are going to find the tangent plane equation and normal line to the ellipsoid, the one on above the equation, at -2, 1, -3. So basically, to find the tangent plane equation, we need to set up our functions, which is, I think, obvious for obvious reasons that we can set up this is as a f, our f. So we can set up f x, y, z equal to this, and then we find all partial x, partial y, partial z, and then put this equation, and then put into the previous tangent plane equation, and just that's the solution. Okay. So we put let's say we partially derive, but since it's separate each x, y, z, so it's quite easy, right? So this is so we only need x, so -2, so this is -1. I don't know why this is so sensitive. So this will be 2. Fz will be 2/9z. This will be -2/3. So then we can set up tangent plane. Oops. Okay, so tangent plane is -1, x minus, so +2, and then +2, and y -1, and then minus 2 over 3 z plus 3 equals 0. And then that's it. Okay. If you want to simplify, you can simplify it. If we want, we can multiply by 3 to remove the fraction here. So this will be 6, this will be 3. So we have 3x negative 6y, right? Plus 2z plus 18 equals 0. So I move all to the side, or I multiply all with negative. And then to find the normal line, we can use the symmetric equations, which we can basically just write down this equation like this. Because all the information we already have. So basically we just write, so this is the tangent plane. This is the symmetric equation of normal line. Okay, just a summary on the property of the gradient factor. If the function differentiable and the gradient factor is not 0, this x is not variable x. This is symbolize the factors. Okay. So the directional derivative of f at x in the direction of vector u is given by this directional derivative. Okay. This is summary for what we have. So the gradient or the del dot the u remember is a unit vector. A unit vector. So if you have been given vector, then you need to change into the unit vector. And then the del in the direction of maximum rate, we can simply take this its magnitude of vectors. Okay, you remember magnitude of the vectors. Okay, and then from the previous tangent plane and the r prime, we see that the del f will always perpendicular, or you can say this del f is the normal. Okay, so this is normal vector. And if it's the plane, then this is normal vector. Okay, perpendicular. Okay, so it's always perpendicular to the level curve or the surface through the x or through the vector.
So like when we find the tangent plane on one point, so the tangent plane will like pass through
that point, yes. So the plane, like here, like this picture, the plane and this point is on the same same. So it's actually like tangent is touching on one point, right? In the 3 dimension, it's become the plane. Like maybe if you have this like this, okay? So you have something. Maybe one side is like this surface, and this is the plane. So it's touching on this point here.
So like how about the normal line?
The normal line means it is going to be perpendicular. So it's actually like this, perpendicular to this surface or to the plane. Yeah. Okay, so I think I can give you this to let you know the score and to let you know whether you can consider take the makeup exam.